Hello everyone. In this class, we will learn Joule-Thomson effect. What is Joule-Thomson effect? It was an effect that was observed by two people, Joule and Thomson. It is actually when a gas expanded, when a gas expanded from high pressure region to low pressure region. So it's going from high pressure region, high pressure region to low pressure region. But there is a condition here. The gas is expanding basically because when you have a high pressure, the volume occupied is less. When it is going to low pressure area, the volume will be higher generally. So here, but the expansion is done through a porous plug. It is through a porous plug. And what is observation? Many gases suffered cooling. So most of the gases suffer cooling except hydrogen and helium at normal conditions. And those two gases also undergone cooling when this process was done at sufficiently low temperature. So any gas can be made into a cooler gas. Maybe in the further process they can be liquefied, provided if that gas is expanded in a Joule-Thomson fashion at a sufficiently low temperature. Let's decide what is that actually. So what is Joule-Thomson effect? Joule-Thomson effect is basically expanding the gas from high pressure region to low pressure region through a porous plug, and there is no heat changes involved in that. So whatever the expansion is happening, that is happening at the expense of its own internal energy. Now let's see what is that actually. Okay, let's take a gas which is confined in a high pressure region, and let's say this is a porous plug. This is a, my drawing is very poor. Okay, this is the area. So let's say we have pressure P1, V1 and temperature T1. So here we have P2, V2, temperature T2. So here work is done on the gas, here work done by the gas. So in this region, work done on the gas, here work done by the gas. And one more important thing, there will be no heat transactions from outside. So therefore basically in this experiment Q equal to 0. So now if we apply the first law of thermodynamics, that is delta E is equal to Q plus W. As we know Q equal to 0, and we simply end up with delta E is equal to W. What is delta E? Change in internal energy. So let's say initially it has an internal energy U1, and after the expansion it has an internal energy U2. Therefore, let's say E1. So E1 and E2 are the initial and final internal energies. That gives us delta E is equal to E2 minus E1. So we can substitute this one here. So what is the W we have to uh, find out? So let's say when the gas, when the work is done here and the gas is expanding, let's say this piston moves here. So this is a volume change. So here if you see basically in this compartment side, volume is completely lost. Therefore we can say the final volume is uh, 0. Therefore initial volume is V1 and final volume is 0. Therefore volume changes uh, minus V1. So therefore what is the work done here? The work done here on the left hand side of the porous plug, that's equal to uh, negative P1 V1. Okay, W1, that's which is equal, I can say this is work done on the gas. How do we get this? Let's see this one. So W is equal to, we know that uh, P delta V. Okay, that's P times 0 minus V1, which is equal to P, and in this region the pressure is P1, so work is done against the pressure P1, therefore negative P1 V1. So here, as it is a work done on the gas, it should be a positive side. On the other side, the work done is, let's say, W2, that's going to be uh, initially we have uh, okay, so I made a mistake here. This is minus P delta V is the formula for the work, and that makes, okay, minus P delta V, this is minus and this makes plus. And other side of the work is negative P delta V is the expression for the work, that's going to be negative P2 times initial value is 0 and finally it is expanding to V2 value, therefore finally V2 minus 0, that's going to be negative P2 and P2. Therefore, what is the net work done? The net work done, W is equal to P1 V1 plus minus of P2 V2, that gives you a negative P2 and V2. And we know that the net work W is equal to delta E. So if we substitute what is this delta E and W, we get E2 minus E1 is equal to P1 V1 minus P2 V2. And if we rearrange this, we get E2 plus P2 V2 is equal to E1 plus P1 V1. And what is this E plus PV is known as? That is enthalpy. Therefore, that is H2 is equal to H1. So from this we can say H2 minus H1 is equal to 0, and we can say that delta H is equal to 0. What does it mean? When a gas is expanding adiabatically, remember Joule-Thomson effect is an adiabatic process where there is no heat changes between system and surroundings. The gas is expanded adiabatically from a high pressure region to low pressure region through a porous plug. And what is the observation? Most gases shown cooling effect under normal conditions. What are the normal conditions? Temperature, normal temperature like 20 degrees. Except two gases. What are they? Hydrogen and helium. They have not shown the cooling effect. Instead, they have undergone heating effect. So, even these two gases that have shown the heating effect at normal conditions in the Joule-Thomson experimental conditions, those also shown cooling effect if this experiment was done at extremely low temperatures. So there is something with respect to this temperature where we need to carry out this Joule-Thomson experiment decides whether a gas undergoes cooling or heating. So, but under normal conditions, which are ambient conditions, most gases show the cooling effect in Joule-Thomson effect except hydrogen and helium. Now, as we already learned that it is an adiabatic process, there is no heat transaction between system and surroundings, there is no heat going out, there is no heat coming in. And also, we proved in the process delta H is equal to 0. What does it mean? It is also a isoenthalpic process. So here there is no change in the enthalpy of the process. Isoenthalpic process. There is no change in the enthalpy of the system in the process. Therefore, we can say that Joule-Thomson experiment is a isoenthalpic process, a process that is happening without change in the enthalpy of the system. Okay, now we know what is the differential of the enthalpy. Now let's go to that one. Let's take enthalpy as a function of pressure and temperature. Okay, but we know that enthalpy is only a function of temperature for ideal gases, but for real gases it also depends slightly on the pressure. So therefore, what is the differential for this? dH is equal to, let's write that one. So that is dou H over dou P at constant temperature times dP plus dou H over dou P at constant pressure times dt. As it is isoenthalpic process, it is an isoenthalpic process. What does it mean? There is no change in enthalpy. That means dH equal to 0. Let's substitute here. So that gives us 0 equal to dou H by dou P at constant temperature times dP plus dou H by dou T. And what is this dou H by dou T at constant pressure? That we already know, that is heat capacity at constant pressure. So therefore I can simply write this one as CP dt. And if we do simple mathematics here, so we get I can say Cp dt is equal to negative dou H by dou P at constant temperature times Tp. So if I make small algebraic changes here, I get uh, dt is equal to negative 1 over Cp times dou H over dou P at constant temperature times Tp. So this is the temperature change that involves in Joule-Thomson effect. So for this I can make it delta H. That's going to be negative dou H by dou P. I will put this in the numerator times dP divided by C. Sorry, this is not delta H, this is delta T. What does mean? The temperature change in the Joule-Thomson effect. So that's going to basically depend on what is the heat capacity at constant pressure for that, and how much pressure change we are creating between the high pressure region and low pressure region, and what is the change in enthalpy with respect to the pressure at constant temperature. Okay, now if we do this one from here, I can say, so we write dt over dP is equal to negative 1 over Cp times dou H over dou P. And what is dt by dP? This is known as a Joule-Thomson coefficient. This is known as dP, sorry, not dP, dt over dP is known as Joule-Thomson coefficient. And what is the expression we got for that? Negative 1 over Cp dou H by dou P at constant temperature. And remember, we have discussed in the previous classes, enthalpy of an ideal gas is only a temperature dependent. It doesn't depend on the pressure. Therefore, this is going to be 0 for ideal gases. For ideal gases, so mu Jt, that is Joule-Thomson coefficient, is going to be clearly 0. But for real gases, it is not 0. Okay, so therefore this is very important equations from which we can find out behavior of the gases. So why Joule-Thomson effect is very important? Because by using the Joule-Thomson effect, so the adiabatic constant enthalpy process will result in cooling of the gases, and if we perform one more cycle of cooling, the temperature of the gas further goes down, and if we do it repeatedly, the gases can be liquefied, and this is the basis for the liquefaction of the gases in one of the process like Linde's process or Clark's process. I don't remember correctly, but this is the process where the continuous cycle of cooling and again undergoing the Joule-Thomson expansion resulting into the liquefaction of gases is also one of the liquefaction technique that uses the Joule-Thomson effect. So what is most important about Joule-Thomson effect is most gases undergo cooling when they are allowed to expand adiabatically from high pressure region to low pressure region to a throttle, which basically which is porous plug. Only hydrogen and helium do not undergo cooling, they undergo heating. So we will talk about remaining things: inversion temperature and effect of real gas in the Joule-Thomson effect. We know that ideal gases do not undergo any kind of changes because their enthalpy and internal energy clearly depends on temperature, and there is no changes in enthalpy at a constant temperature. Therefore, Joule-Thomson effect, uh, mu Jt, Joule-Thomson coefficient for ideal gas is going to be zero, but it's not zero for the real gas. Real gas Joule-Thomson effect has this value. So, mu Jt is equal to 1 over Cp times 2a over RT minus. So this is the Joule-Thomson effect coefficient for real gas. This is for real gas, and this is equal to 0 for ideal gas. And how we arrived at this equation, that is the topic for the next class. We will derive this equation. What is that? Joule-Thomson coefficient for real gas in the next class. And this is for today's class. Thank you very much.